So we're back to matrices. That's been a long time since we've seen a matrix. All right. So if I've got a directed graph, which this is a directed graph because it's got arrows, right? So arrows on the edges, a directed graph. So the adjacency matrix, it matches the graph. So each one of these entries, so Aij means like this would be V11, right? Or I'm sorry, A11. So this would be the number of arrows from V1 to V1. So looking here, I can see there is one edge from V1 to V1. And so that's why there's the number 1 there. So let's look at the next one. So this would be the number of edges between V1 and V2. So between V1 and V2, there's none, right? Because this is a directed, so there's no arrow going that way. So there's a 0. And this would be the number of edges between V1 and V3, and there's none. So that's why there's a 0 there. Okay, if I went to this here, this entry would be the number of arrows from V2 to V1, and I can see there's one edge right there. And this would be the number of edges between V2 and V2. There it is, got the loop, right? And then this would be the number of edges between V2 and V3. So V2 and V3, I see 2 different edges, so that's why there's the number 2 there. Okay, so I think you've got that idea. So let's go do this one. So this is saying this is a matrix for a directed graph. And I forgot to mention, if there's 3 vertices, it's going to be a 3 by 3 matrix. So here we have a 4 by 4 matrix. So I know there's going to be 4 vertices. So let's just start off by drawing the 4 vertices. And leave enough room so that you can draw all the arrows in between them, right? So V2, and then here's V3, and V4. Okay, so this here, this 1, is saying there's one edge between V1 and V1. There it is. So it says it's a directed graph, so I just have to put the arrow there. And then between V1 and V2, there's nothing. Between V1 and V3, there's one arrow. And then between V1 and V4, I've got 2 edges, and it's directed, so I've got that. All right, let me try and do different colors, so hopefully this helps. So these are all where the vertex V2 is going to. So the only one it goes to, V2, goes to V3, has one edge to V3. That's what that stands for. So let's move on to the next one. So these are all the places that the vertex V3 is going. So V3 is going to V2 with 2 different edges. So V3 to V2 with 2 different edges like that. And then V2 is also going to V3 is also going to V3. So it looks like that. And V3 is also going to V4. Last row here. So I've got V4 is going to V3 with 1 arrow. And there it is. So that's your directed graph from the adjacency matrix. Okay, so now this example, they're telling us it's undirected, and you can kind of tell that because there's no arrows anywhere, right? So we need to put together the matrix. I can see there's 4 vertices, so it's going to be a 4 by 4 matrix, right? So this first entry will be the number of edges from V1 to V1. There's 0. And then this one will be the number of edges between V1 and V2. That would be 1, right? That edge right there. Between V1 and V3, well, there's no edge, so that's a 0. And then between V1 and V4, and so there's 1 edge there. So that's our connections for V1. So then if we move to vertex V2, so V2 has an edge going to itself, right? Has the loop. This is V1. V2 to V1. That would be this edge. So the 1 here comes from this. V2 to V2 is the loop. And then V2 to V3, is there any edges? Yes, there are. There's 2 edges going between V2 and V3. And are there any edges going between V2 and V4? There is. There's 1. All right, moving down to the next one. So moving to vertex V3, that's what this third row would be. So V3 to V1, nope, there's nothing there. V3 to V2, yes, I see two edges. V3 to V3 to V3 itself, nope, no loops there. And then V3 to V4, nope. All right, so then the last one would be what our V4 vertex is doing. So V4 to V1, yes, I've got one edge. V4 to V2, yes, I've got one edge. V4 to V3, no, nothing happening there. And then V4 to V4, yes, I've got that loop. So there's one edge there. Okay, so if I take that matrix, that adjacency matrix, that's what it's called, and I square it or cube it, and I'll give this to you, you won't need to multiply these things out. What this uniquely tells us, if I have a cubed, then I can figure out how many walks, how many ways that I can get to or from V2 to V2, and that has length 3. So this is key. So if it's a cubed, this will tell me the number of walks of length 3. And then if I want to identify from which vertex to which vertex, from V2 to V2, well, that would be this number 4. So let's just kind of go through a couple of examples. So here is a to the 4th power. So this is going to give me walks of length 4. And so I need to identify the entry from V2 to V3. So from V2 to V3, that would give us 7. And here is a squared. So we're going to get walks of length 2. And so how many are there from V3 to V2? So V3 to V2, I would get 5. And and I forgot to do part B here from this one. So walks of length 4 has to be a to the 4th. From V3 to V1, there would be 11, right? That number right there.